welcome to this unit where we're going to explore the derivative. And then the first section, we're going to look at limits. So a limit is just a tool that we use to describe the behavior of a function as the values of x approach or become closer to some particular number. So let's take a look at what a limit is. What happens to f of x equals x squared when x is a number very close to but not equal to 2? So what I did was I created a table, and we can see here that we have x values that are close to 2. So down here we have 0.1 away. 2 plus 0.1 gives you 2.1. And then we just add a 0 each time. And as we do that, we're getting closer and closer to the number 2 from this side. And then over here, I subtracted 0.1 and got 1.9. And I added a 9 each time. And again, as you go towards 2 from the left, you're getting closer and closer to 2. Okay, now we want to figure out what these values are. And one of the easiest things to do is to go on your calculator, and I'm going to use this app here. It's called Calculate 84. It's very similar to the TI-84 Plus calculator. And I'm going to type this into y equals, and we'll just type in x squared. Okay. And then what I'm going to do is I'm going to go into second window, which is table set. And we want to make the independent variable, which is your x variable, we want to change it from auto to ask. And then we're going to go and hit second graph, which is going to take you to the table. And all you have to do is plug in x values and it will give you the y value. So for example, the first x value far off to the left is 1.9. So 1.9 squared is 3.61. If I go to the next line, so hit the down arrow, and now I'll type in 1.99, you get 3.9601. Okay, and you would keep doing this for all of the values. And we're going to plug those into y equals. And these are the values that you should get. And you'll start to see some patterns as you're filling this in. So what I would like you to do is investigate here as x gets closer to 2 from either side, so from the left or from the right. What is f of x getting closer to? So as you notice, as x gets closer to 2, f of x is getting closer and closer to 4, right? Which is not surprising because when x equals 2, f of x equals x squared is 4 because 2 squared gives you 4. So what we say here is the limit, and the abbreviation for limit is LIM, of the function f of x as x approaches 2 is equal to 4. Okay, and I'll write that out for you so you can get used to the wording. Okay. So we've got one-sided limits, which is the limit from the left. Okay, so as we approach 2 from the left-hand side, the way we would abbreviate that is using a negative above the 2. And we can see as we approach 2 from the left that f of x is approaching 4. So the limit of f of x as x approaches 2 from the left is just 4. And if we want to look at the limit from the right, we would just put a little plus above our 2. And again, as x is approaching 2 from the right, f of x is getting closer and closer to 4. Okay, so we're going to put those two things together. Since the left limit and the right limit are the same, we can just use this two-sided limit, which takes into account both, where we would just say the limit of f of x as x approaches 2 is 4, where there's no need for that negative or that positive. So a two-sided limit exists only if both the one-sided limits exist and they're the same. Okay, so that's very important. So we see this here, that the limits from the left and the right, they both exist. We're going to see times when they don't exist, and they are both the same. So therefore, that two-sided limit exists. Okay, so I'll put a little notation here. Exists only if both one-sided limits exist and are the same. So here's an informal definition of a limit, and the reason we call it informal is because we're going to use terms like closer and closer, or can be made as close to L, but we're not actually defining that. So let f be a function and let a and L be real numbers if, as x takes values closer and closer but not equal to a on both sides of a, the corresponding values of f of x get closer and closer and perhaps equal to L. So in our last example, a would be the 2. As x gets closer and closer to 2 from either side, right, it's approaching and also equal to 4, and 4 would be L in that instance. The value of f of x can be made as close to L as desired by taking values of x close enough to a. And we see that in the table because we took values that are close to 2 in either direction. Then L is the limit of f of x as x approaches a, and then that's how we would write it, as we kind of discussed. Okay, please keep in mind that the limit is a value of y, not of x. Okay, let's look at another example. So here we would say the limit of g of x as x approaches 2. We want to find that where g of x equals x cubed minus 2x squared divided by x minus 2. So again, I created a table and it's set up similar, if not identical to the last table, because we're still looking at the limit as x approaches 2. So we picked values that are close to 2 on either side. So again, you would go to your calculator. We'd want to go to back to y equals and clear out what's in there. And we're going to type in the following function. So I want my fraction bar. So I'm going to hit alpha y equals. And then the first one that pops up there is the fraction. And I'm going to type in x cubed minus 2x squared. Let me clear that. Okay, so we've got x and then cubed minus 2x squared. And then in my denominator, I have x minus 2. Okay. Now I want you to look at this for a second, and we are looking at the limit as x approaches 2. So if you look at this function very carefully, the value of 2 could cause a problem. And again, we're assuming we already have the table set up already, but we can check it. You would go to second window, make sure the independent variable, which is your x variable, says ask, so that you can type in the values that you used in your table. And then we're going to go to second graph, which is the table, and we're going to plug in our numbers. So when I plug in 1.9, I get maybe we have to do this again. Oh, we have to hit enter for our function and then go here. Okay, now we'll type in 1.9 and hit enter. Nope, that's still not right. Okay, let's see, second table. Let me clear that. We might have to delete what's in here. Yeah, that's what you have to do. At least if you're using the app, you have to click delete. Okay, let's try it again. Oh, I guess that is correct. It's 3.61. Let's see what the next one gives us. 1.99. Yeah, this looks like it's correct. So, okay, so we get 3.61. And then 3.9601, and so on. Now, when you plug in 2, let's go do that so you can see what happens. You get an error, right? So why would 2 give us an error? Because if you look in your denominator, 2 minus 2 gives you 0, okay? So that's a problem. We know that that would be undefined. And then if you plug in the other values, you get the following. So the table suggests that the limit as x approaches 2 of g of x would equal what number? So from either side, as I approach 2 from the left or I approach 2 from the right, it appears that the limit is going to equal 4 because the numbers are getting closer and closer to 4, despite the fact that g of x doesn't exist at x equals 2, right? Because it would make the function undefined. So let's use some algebra and figure out the limit this way. Instead of making the table, this is another technique we can use to evaluate a limit. So we're going to take our function, and one of the things we can try doing is factoring. And if you factor the numerator, you're going to end up with x squared times x minus 2. And in the denominator, you would also end up with x minus 2. And if you remember from the last chapter, we've got our x minus 2's, they cancel out, right? So there would have been a vertical asymptote at that value of 2, but we removed it. There's now a hole, right? So keep that in mind. What we're left with is just g of x equals x squared, okay? Now, we know from looking at the table that it's approaching 4, which makes sense. So we would say the limit as x approaches 2 of g of x is equal to the limit as x approaches 2 of x squared, because that's what g of x is, and 2 squared is 4. Okay, we can also use a graph, so we can take a look. We know that there's going to be a hole at 2 comma 4, so I can automatically put that in. And we can plug in some values for x squared, which we know, like negative 2 squared gives us 4, negative 1 squared is 1, 0 squared, 1 squared, and so on. And we're going to end up with, you guessed it, a parabola, right? Because it's x squared. And one of the things you should notice here, as you approach 2 from the left, and you approach 2 from the right, if we go up, y is going to approach 4. Okay, that is the value of y right there. Okay. So what I'd like you to do is pause the video, and you can try finding the limit for the next function, and then you can unpause it when you're ready to move on. Okay, let's look at example number 3. So here we want to determine the limit of h of x as x approaches 2 for this function. And we call this a piecewise function. It's a function that's defined by 2 or more pieces. So here we have h of x is going to equal x squared if x doesn't equal 2. And h of x will equal 1 if, if x equals 2. So let's graph what this is going to look like, okay? We know that if we graph x squared, it's going to look something like this. Okay, and again, it says h of x will equal x squared as long as x doesn't equal 2. So that means 2, when I plug in 2 and I square it, I get 4. I need to put an open circle there because x can't equal 2. So here's my parabola. We also know that h of x will equal 1 if x does equal 2. So that just tells me that I'm going to graph the point 2 comma 1. Okay, so 2, 1 looks something like that. Okay, so it's like a random point there off to the side. Sorry, and it should move down 1. Let me fix that. 2, 1. Okay, there we go. All right, so let's take a look at this. Let's look at the one-sided limit. How about the limit as x approaches 2 from the left? So as I go from the left and I approach 2, which is right there, okay, and then I go up, I can see that the limit is equal to 4, right? So as I go up to my curve, I get 4 for my answer. So the limit as x approaches 2 from the left of h of x is equal to 4, okay? And as I approach it from the right, it's the same thing. If I go up, I can see that it's equal to 4, right? As I approach 2. Okay, so it's also equal to the limit as x approaches 2 from the right. It's the same thing. So since h of x approaches 4 as x gets closer to 2 from both sides, okay, that tells me that the limit as x approaches 2 of h of x is equal to the limit as x approaches 2 of x squared, which is equal to 4. Okay. Let's take a look at another example. So here, we want to find the limit as x approaches -2, and we can see that f of x is equal to 3x plus 2 over 2x plus 4. All right, so let's first make a table to do this. And we just plug in our values. This time we're looking at -2, right? So if I add 0.1, I get -1.9, and I'm just going to add a 9 each time. And -2 minus 0.1 gives me -2.1, and I just keep adding a 0 each time. And you're going to plug that into the table the same way I've been showing you, and you should get the following numbers. Okay, and then this is going to be a big number here. Okay. So as you look here, what is something you notice as you approach -2 from the left, and then as you approach -2 from the right? So as x approaches -2 from the left, f of x is getting larger and larger, right? Without any boundary, it would keep getting larger if you think about it. So if I was to, plug in -2.00001 and so on, it's going to keep getting larger and larger. And because as x approaches -2, the numerator is going to approach -4. If I plug in -2 into my numerator, into x, I would get -4, okay? And the denominator, if I plug in -2, 2 times -2 is -4, plus 4 gives me 0, right? So that's a problem. So if we look at the one-sided limits here, the limit as x approaches -2 from the left of f of x, we said is going to keep getting bigger and bigger and bigger. So that means it's approaching positive infinity. The limit as x approaches -2 from the right, on the other hand, so as we go from the right towards -2, it's getting bigger and bigger and bigger towards negative infinity. Now notice that both of my limits, my one-sided limits, are not the same. So that tells me then that the limit as x approaches -2 of 3x plus 2 over 2x plus 4 does not exist. Because in order for the limit to exist, remember there's those two things. If both the one-sided limits exist, which they do, and are the same, and they're not the same. So therefore, that tells me that the limit does not exist. And you can write DNE for does not exist. That's an abbreviation for that, okay, since the limits are not equal. Okay, you can try the next one. In the next one, it's an absolute value. And you can also try creating your own table for that one, okay? And then you can unpause the video when you're ready. So the existence of limits up to this point can be summarized in the following ways. And you can pause the video rather and read through that box there, and then unpause it when you're ready to move on. So the limit of f as x approaches a may not exist, right? If f of x becomes infinitely large in magnitude, as it did in that last example I did, as x approaches the number a from either side, the limit does not exist. In addition, we have these following little clauses. If f of x becomes infinitely large in magnitude in the positive direction as x approaches a from both sides, we would write that the limit as x approaches a of f of x is infinity. If f of x becomes infinitely large in magnitude in the negative direction, we're just going to say that it equals negative infinity, okay? If the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x equals m, and L doesn't equal m, then the limit as x approaches a of f of x does not exist, right? Because we said earlier, this goes back to what we said previously, that both one-sided limits have to exist, but they also have to be the same. So they both exist, but they're not both the same. And that's what happened in that last example as well. Okay, so to summarize here, a limit exists if f of x approaches the same number as x approaches a given number from both sides. The limit does not exist if f of x approaches positive infinity or negative infinity, and if the limits from the right and left are different. So here you can see some examples of that, like in this graph here, as x approaches -6 from the left, f of x is getting increasingly large in magnitude. It's approaching positive infinity, and from the right, it's getting increasingly large in magnitude in the negative direction. So it's approaching negative infinity. Since the left and right limits are not the same, that means that the limit of that function does not exist. So here's some rules for limits. Let's talk about these. These are going to be some time savers for everyone. If you know how to apply these rules, which we'll do here in a second, it'll save you time so that you don't necessarily have to make a table or even look at the graph. So take a minute and pause the video and read through these rules here, and then you can unpause it when you're ready to go over it. Okay, so we have two examples here. We've got function f and function g, and the limit of f of x as x approaches a is going to equal capital A, and the limit of g of x as x approaches a is going to equal capital B. So we have what's called the constant rule for limits, and this just says if you take the limit of some constant, which is just a number, as x approaches a, the limit just equals that number. Here we have the constant times a function rule for limits. So if k is a constant, remember a constant's just a number, the limit of k times f of x as x approaches a is just the same thing as taking the constant out of there and multiplying it by the limit. Okay, here you have the sum or difference rules for limits, and you're taking the limit of f of x plus or minus g of x as x approaches a, and here notice that the rule for limits allows us to split the two limits up, okay, separately. And we have something very similar for the product rule for limits, where you can split the products up, as well as the quotient rule. You can take the limit of f of x over g of x and split it into the limit of f of x over the limit of g of x. You have a polynomial rule for limits. So if p of x is a polynomial, then the limit of p of x as x approaches a is just whatever p of a is. So it's kind of like you're just evaluating the polynomial at that value of a. The power rule for limits is the limit of f of x to the k power. So for that one, it's just going to equal a to the k power, provided the limit exists. You have the exponent rule for limits. So for any real number where b is greater than 0, right, the base has to be positive, of course. The limit of b to the f of x is just the same thing as b to the limit of f of x as x approaches a, which is going to be b to the a. So you would just solve this and find the limit, and then take the base to that power that you just found. And then you've got a logarithm rule for limits. So this one is just the limit of the log of f of x is just the same thing as the log of the limit of f of x, as long as a is greater than 0, right? Because you can't take the log of a negative number. If you remember from college algebra, pre-calculus, those kind of classes. The domain for logs is just all positives. And 0, of course. So x has to be greater than 0. And then you have the equality rule for limits here. And this is just saying the limit of f of x is going to equal the limit of g of x if f of x equals g of x. So let's apply some of those limit rules to these problems, and we'll see how useful they are so that we don't have to make any kind of table. So here we have an example 5. They tell us that the limit of f of x is equal to, the limit of f of x as x approaches 2 is equal to 3, and the limit of g of x as x approaches 2 is 4. Use the limit rules to find the following limits. You might want to have the limits off to the side so you can kind of refer to them. So here I see that I have the sum of these two functions, and I'm taking the limit, right? So the sum rule for limits allows me to split this up. So I'm just going to split this into the limit as x approaches 2 of f of x plus the limit as x approaches 2 of 5g of x. Now, I also know there's what's called the constant times a function rule, which is what I have here. I have a constant 5 times g of x, which is a function. So the constant times a function rule allows me to pull that 5 in the front there. So I would have the limit as x approaches 2 of f of x plus 5 times the limit as x approaches 2 of g of x. And I know from my given information, the limit as x approaches 2 of f of x is 3. So this is just going to be the limit as x approaches 2 of 3 plus 5 times the limit as x approaches 2 of 4, since that's what g of x is. And here I'm dealing with the very first rule for limits, where I'm taking the limit of a constant, so I know that the answer is just going to be 3. And then for 5 times the limit of 4, I know 4 is a constant, the limit of 4 is just 4. So it's going to be 5 times 4. And if I simplify that, I get 23. Let's look at letter B. So in letter B, we are dividing, which is a quotient. And we also have a natural log, the ln of g of x, right? So I'm going to split this. I've got the limit as x approaches 2 of f of x squared. And I'm going to divide that by the limit as x approaches 2 of the ln, or natural log of g of x. And the quotient rule for limits lets me do that. Okay, now if you notice, we've got a power here. So we can use the power rule. We can just simply write this as the limit of f of x as x approaches 2, and we're going to square that entire piece there over, and we'll leave this as just, actually to make this easier, we can pull out the ln. We can use our log rule. We could take the ln of the limit of g of x as x approaches 2. And we know that the limit as x approaches 2 of f of x is just equal to 3. So I'm going to replace that part with the 3, and it's 3 squared. And then I've got on the bottom the natural log of the limit of g of x, and I know g of x is 4. So on the bottom I have the natural log of 4. And you would need a calculator for this. You've got 9 divided by, and if we go to our calculator, clear that. The natural log is to the left of the 4, so you would type in the natural log of 4, which gives me 1.3863. So now you would just need to divide 9 by 1.386. You can even carry it out a little bit more, the 29. And when you do that, you end up with 6.492. Okay, so now you want to pause the video and try the next problem on your own, and then you can unpause it when you're ready to move on. All right, let's look at example number 6. So here we're looking at the limit of this function as x approaches 3. And again, we're going to try to use our rules here, okay? So if I notice I have a quotient, so I'm going to split this up into the limit of x squared minus x minus 1 as x approaches 3 all over the limit of the square root of x plus 1 as x approaches 3. And in the numerator, or in the denominator rather, I can apply my rules for limits. So I'm just going to leave the numerator alone. But in the denominator, I can actually take the square root of the limit as x approaches 3 of x plus 1. Okay, so all I'm going to do here is I'm going to now plug in my 3. So I'm going to have 3 squared minus 3 minus 1 over the square root of 3 plus 1. Okay, and if you're wondering why am I not writing the limit, why, do I need to do that? Well, because if you're plugging in 3 for x, that's a constant. You're going to end up with a constant. So the limit of a constant is just whatever that constant is. And here I get 9 minus 3 minus 1, which gives me 5. And in the denominator, I get the square root of 4, which is 2. So that's just equal to 5 halves. A lot of limits can be found just by evaluating. So as long as there's no rules that are broken, right? Like division by 0, I'd want to check and make sure when I plugged in this 3 that it didn't give me a 0 in the denominator, because that would be a problem. Or as we said earlier, like the log of a negative number, you don't want that either. Okay, let's try it for this next one for letter B. So I'll give you an example of when you got to be careful. So in the next problem, we're looking at the limit of that function as x approaches 2. And something I want you to notice here is if you were to place the 2 inside, right, for a second, you would get 2 squared plus 2 minus 6 over 2 minus 2. Because essentially that's what we did in the last problem. In the numerator, I would get 0, and also in the denominator. So now you have this new fraction, 0 over 0. We call that indeterminate form. So the method we used in the last problem isn't necessarily going to work, where we just substituted the value of x in and got an answer for our limit. Here we can't do that. So what we can do instead is we can try simplifying. If you take a look at x squared plus x minus 6, it does factor. So what I'm going to do is factor it. And if you factor x squared plus x minus 6, you get x plus 3 times x minus 2, and then over x minus 2. And as you can all see, the x minus 2 factors disappear. So all I'm left with is just x plus 3. So now I'm going to try to take the limit as x approaches 2 of x plus 3. And now if you plug in 2 and add 3, you get 5. In letter C, if we try plugging in the 4 first, you're going to see again that you're going to end up with indeterminate form. So that means we have to simplify this somehow. And you can see it can't be factored, right? So what I'm going to do is I'm going to try instead rationalizing, which you may remember if you took intermediate algebra, college algebra. Essentially, rationalizing is a technique that we use to get rid of any kind of radicals in the numerator or denominator. So we're just basically manipulating the expression and making it look different, okay, so that we can figure out a way to get it to work out. So to do that, I'm going to multiply by something called the conjugate. So if I take the square root of x minus 2 divided by x minus 4, the conjugate of the square root of x minus 2 would just be the square root of x plus 2. And I'm going to multiply that in the numerator and denominator because this really just equals 1. So all we're doing, like I said, is changing this. We're rewriting the expression, we're disguising it. We want to get rid of this radical in the numerator, which is why I am rationalizing the numerator. If the radical is in the denominator, then you'd want to rationalize the denominator using the same process. So now if I want to multiply these, what I'm going to have to do is I'm going to have to distribute. So FOIL, right? I'm going to multiply the square root of x times the square root of x, which just gives me x. And then the square root of x times 2 is 2 square root of x. Negative 2 times the square root of x is negative 2 root x, and negative 2 times negative 2 is negative 4. And then I'm going to divide that by, again, we're going to FOIL. Well, actually, we don't even have to FOIL the denominator, and I'll show you why. So let's just leave it like this. Okay, and this will make it easier for you. If you FOILed the denominator, it's not wrong. It's just you're doing more work because those two terms are going to cancel. And we're left with x minus 4. And in the denominator, I'm just going to rewrite what I have there, which is just x minus 4 times the square root of x plus 2. And if you notice, the x minus 4s are going to cancel out. Okay, so what I'm left with now is the limit as x approaches 4 of my new function, which would be 1 over the square root of x plus 2. And now try plugging in the 4, and you end up with 1/4. So when you use algebra to simplify limits, there's always a little caveat. You need to make sure you're not breaking any rules, right? Where, plugging in a value is not going to give you a 0 in the denominator, or if you have a logarithmic expression, right, which includes natural logs, ln's, you don't want to have a negative argument. So we need to address those issues before we can solve them. And in the last example, we addressed it by factoring, which eliminated the piece that turned the fraction into a 0 in the denominator, and then also the numerator. And then in this last example, we rationalized, which changed the form of the expression, which allowed us to be able to evaluate it at x equals 4 and then find the limit that way. So you can pause the video and practice these next few problems, and then you can unpause when you're ready to move on to the next example. In this next example, we're asked to find the limit of that expression as x approaches 1, and we want to create a table. Okay, so let's look at our table here, and then we'll also evaluate the limit in other ways. All right, so we know that x approaches 1, we're going to put the 1 in the center of the table. And then what I'm going to do is I'm going to add 0.1, and that's going to give me my number to the far right. And all I'm going to do is just add a 0 each time, as I get closer and closer to 1. And then I'm going to subtract 0.1, which gives me 0.9. And I'm going to add a 9 each time. And that's going to get me closer and closer to 1 on the left side. And then you're going to plug that function into the calculator, use the table, as I showed earlier in the video, and then you're going to get the following values. So as you can see here, as x approaches 1 from the left, the f of x values are getting larger and larger in magnitude in the negative direction. And as x approaches 1 from the right, the y values are getting larger and larger in terms of the positive direction. If we were to plug in 1 also into the numerator, we would get 0, and in the denominator, we would get 0. So we would get indeterminate form again. There's another problem. So let's try factoring, which is a technique I showed you earlier. If I factor the numerator, it's just going to be x minus 1 squared. And then in the denominator, I have x minus 1 cubed. And I would be left with 1 over x minus 1. Because 2 of these are going to go away, you'll be left with 1 in the denominator. So now, if I was to try to take the limit as x approaches 1 of 1 over x minus 1, try plugging in the 1, you would get 1 over 0, which is undefined. Okay, if we use the table like I said, the limit as x approaches 1 from the left of, we'll just call it f of x, is negative infinity, and the limit as x approaches 1 from the right is positive infinity. So that's not helpful either. If we look at the graph, we know from the last chapter, we're going to have a vertical asymptote at x equals 1. And we know that we're going to have a horizontal asymptote at the x-axis. And the graph's going to look something like this, which you can graph on your graphing calculator, but it'll give you an idea. So again, as x approaches 1 from the left, f of x is getting larger. You can see that in the table. And as x approaches 1 from the, as x approaches 1 from the right, f of x is getting larger. And then as x approaches 1 from the left, f of x is getting larger, but in the negative direction. So that's why it's negative infinity. So we can see here we're not getting anywhere with this, right? But what I do know is, from earlier in the section, if the one-sided limits are not the same, the limit does not exist. So you really don't have to do any more work for this. What we just determined here was the limit as x approaches 1 of x squared minus 2x plus 1 over x minus 1 cubed is going to be the same thing as the limit as x approaches 1 of 1 over x minus 1. And we know that it dne does not exist. In the next video, we're going to look at limits at infinity.